Want to learn engineering and science? Well, you've tuned in to the right channel. Hit subscribe and press the bell icon and never miss an update from us. Hi guys, what's up? This is your friend and tutor Manas, and in today's tutorial we're going to talk about shear force and bending moment diagrams. I'll tell you exactly how at any given point in a beam or at any given cross section of the beam you can calculate shear force and bending moment. Okay, it's going to be pretty easy, and I strongly advise you all to watch this video right till the end so that you are equipped with all the tools necessary to draw shear force and bending moment diagrams. So here we go. Let's say we have a beam which is simply supported at A and at B. Okay, so the first thing that we need to do is we need to free this beam. All right, we need to make a free body of this beam. Okay, something of this sort. And what I have essentially done is that I have replaced these two supports by these two reactions. All right, in the form of RA and RB. Okay, so we wish to calculate the shear force and bending moment somewhere along this cross section, that is at C. Now for that to happen and to analyze this properly, I'll be separating these two portions. So there is a portion towards the left of this section, that is this portion AC, here it is, and there is one more portion towards the right of this section, that is portion CB. Okay, now let's talk about what the definition of shear force is. Well, it says that shear force is the algebraic sum of all the unbalanced vertical forces acting either towards the left of the section or to the right of the section. Now let's just say that the shear force acting somewhere along this cross section is represented by V, and let's just assume that it is acting in the downward direction. And if you wish to calculate the value of this or the magnitude of this shear force, you can do so by applying simple equation of equilibrium, that is summation of all the forces in y direction is equal to 0. Okay, and that's something that we learn in mechanics in forces. All right, okay, so watch next. If you watch carefully, this shear force has been assumed in the downward direction. Then obviously the shear force acting over here in the portion CB at C will be in the upward direction. Okay, fine. Now let's just assume that the bending moment at this cross section C is acting something of this sort in the anti-clockwise sense. Therefore, in order to nullify this effect, what we'll have is a bending moment in the clockwise sense over to this side. Now again, this bending moment, if you want to calculate, you can easily do so by doing this. Summation of moment at point C is equal to 0. This value can be calculated. Now guys, remember this V dash and this V and V dash, both of them are absolutely same. Okay, you can say that V dash is essentially equal to negative of V. All right. Okay, fine. So this is essentially sort of a sign convention that we're going to be following. If you take this section from the left, shear force downwards, moment anti-clockwise. And if you take this section from the right, shear force upwards and bending moment clockwise. All right. Now, in order to simplify this, let's have a beam. Let's cut the beam. Okay, so we have two portions, one towards the left while the other towards the right. If you take this section from the left, shear force downwards, bending moment anti-clockwise. If you take this section from the right, shear force upwards and bending moment clockwise. All right. Now, shear force and bending moments are internal. All right. Fine. Let me show you one more figure and let me explain you what exactly a positive shear means. If you watch carefully, this is internal. Okay, something which is happening inside the material, and this shear force is in the downward direction, and therefore the external load will be in the upward direction, this way. And if you consider this portion of the beam, shear force is acting in the upward direction, and therefore the external loading will be acting in the downward direction, this way. So the overall effect of these two forces is to produce a clockwise effect, and this in fact is what you call a positive shear. There is something which is known as positive bending moment. Okay, let me tell you what exactly is that. If you watch carefully, towards the left hand side portion, we have an internal bending moment over here. This is anti-clockwise, and therefore in order to nullify its effect, we have a clockwise bending moment over here, this way. Okay, and if you consider this right hand side portion of the beam, you have a clockwise bending moment, and to nullify its effect, we have an anti-clockwise moment. Now both these moments are acting in such a manner that they try to bend the beam in this way. Okay, and this is what you call sagging. And whenever a beam sags, okay, we have a positive bending moment. And whenever a beam hogs, this is what you call hogging. Okay, let me write this, hogging. and this has negative bending moment, and when you speak of sagging, we have a positive bending moment. So guys, essentially you can solve the problems based on beams in both ways. You can take the section from the left or section from the right, but the most important thing in this lecture up till now is this sign convention. Okay, so copy paste this sign convention in your mind so that you're able to solve each and every problem based on statically determinate beams. Now let's take up an example and let's try to apply a method of sections in order to draw shear force and bending moment diagrams for this particular case. So this essentially is what you call a simply supported beam, and what we're gonna do is there are two supports over here at A and at B. Okay, now since the external loading is vertical in nature, therefore the reactions that we're gonna have at A and B are also going to be of the vertical nature. So let me just draw this. Over here we're going to have, let's say, the reaction at A, RA, and over here the reaction, let's say, be represented by simply RB. So immediately I'm going to be using this equation of equilibrium, summation of all the forces in y direction is equal to 0. These two forces upwards and hence positive, so RA plus RB minus this P, okay, minus P is equal to 0. So you can again rewrite this, it's pretty easy. RA plus RB is equal to P. Okay, the next thing, we're going to take moment about the hinge. So the moment about the hinge, what is the hinge? That is point A. Okay, so we're taking moment about this point. Okay, how many forces are there? There are three forces, RA, P and RB, out of which this RA force seems to be passing through point A itself, and A is that point about which the moment is to be taken. Therefore the moment of this RA force is going to be equal to 0, since the perpendicular dropped from A is going to be of 0 length. Anyways, so we have to essentially deal with these two forces, that is P and this RB. So P multiplied by L by 2, that is about A, will give a clockwise moment. So negative of P multiplied by L by 2. Anything else? We've got this RB. Okay, so at point A, this RB produces an anti-clockwise moment, hence a positive sign. RB multiplied by this distance from A to B. Okay, so the overall length of the beam is L, into L is equal to 0. So this is pretty easy. You just need to solve this equation and you are going to get the value of RB is equal to P over 2. And when you put this value of RB over here, you are going to essentially get the value of RA, which is also going to work out as P by 2 only. Okay, so that's it. So these are the reactions at supports. Okay, now we're gonna go ahead and we'll try to apply the method of sections. Method of sections to compute the shear forces at various points across the length of the beam. Okay, method of sections. Now this method of sections is something that you have also learned in trusses. Okay, and what we're gonna do is we're going to take this section from right. And you know the sign convention, whenever you try to take section from the right, from here, that means you'll see that you have a positive shear force and a clockwise bending moment. All right, and this is what you call the distance X. Okay, now let me do this. Let me have a section. Here we go. Let me have the right hand side portion of that section. Okay, so that's the beam, and the first thing that I would do is to place the reaction over here. So this is what you call the RB reaction, whose value has been computed as P by 2. Okay, what else? So this section is essentially at a distance of X from end B. Okay, so over here you're going to have a positive shear force, something of this sort, and a clockwise bending moment. So this is going to be a clockwise bending moment and a positive shear force. Okay, so what we have essentially done, we have taken section between D and B. Okay, let's do the analysis. Now let's apply the static equations of equilibrium for this portion of the beam. Okay, now first of all, I'm going to go ahead and use this summation of all the forces in y direction. Okay, so because only forces in vertical direction are responsible for creating shear forces. All right. So how many forces are we to deal with? We have to deal with Vx, we have to deal with P by 2. Both of them upwards and hence positive. Vx plus P by 2 is equal to 0. So ultimately you can say that Vx is equal to negative of P by 2. Now guys, if you watch carefully, the shear force between D and B is not dependent on X, or you can also say it is independent of X. So the shear force between these 2 points is going to remain same, that is minus p by 2 itself. Hence you can say, or you can conclude, that shear force at B is going to be equal to negative p by 2, and also the shear force at D is also going to be equal to negative of p by 2, right? Okay, so what's the next thing that we can do? We can take the moment. Okay, let me go ahead and take the moment is equal to 0. Okay, so we've got this mx clockwise, hence negative, minus mx. What else have we got? We've got this p by 2 multiplied by x, producing an anti-clockwise moment here at this cross section, plus p by 2 into x is equal to px over 2 is equal to 0. And if you try to frame this equation in a better way, you're going to write mx is equal to px over 2. Okay, now let's see, we want the value of moment at point B. Okay, at point B the value of x is going to be equal to 0. Just think about this, and when you put the value of x is equal to 0 here, so 0 into anything is absolutely 0. Okay, now if you want to find the moment at point D, let's say, okay, so D appears to be at a distance of L by 2 from B. That means the value of x has to be put up as L by 2, and when you put that value over here, that is L by 2, you're going to get the value of moment at D is equal to P L over 4. Okay, right? Now let's go ahead and let's now take the section between what, A and D. Let's do this quickly, A and D. Okay, again, you know that we are doing the sectioning from the right, and here we go. That's the section, and that's the portion of the beam that we're going to be considering. And if you want, here the shear force will be taken upwards positive, and bending moment again has to be taken as clockwise. And let me write this also. This distance, or the distance of the section from the extreme right point of the beam, has to be taken as x. Okay, so the first thing that we should focus on is this: summation of f of y is equal to 0. And if you watch carefully, Vx positive, P negative because it is downwards, and we've got this reaction at B also. So the reaction was P by 2. So these two forces positive and this one negative. So let me just write this: Vx plus P by 2 minus P is equal to 0. And if you can rewrite this, Vx will work out as P by 2 simply. Okay, so previously the value of Vx that was worked out was negative of P by 2, and this time around the value of Vx has been worked out as positive P by 2. Now again guys, if you watch carefully, this equation of this value of shear force is not dependent on x. Therefore, at each and every point between A and D, the value of shear force is going to remain same, that is equal to P by 2, and hence you can say Vd is equal to P by 2, and also Va is equal to P by 2. That's it. Okay, fine. Now let's solve this for moment equation. Moment. Okay, so moment about this point, this section is equal to 0. So we've got this mx clockwise, and hence negative. We've got this p. So this p has to be multiplied with this distance. Now if you watch carefully, this distance over here is x, and this over here is L by 2. So this distance from this section is going to be equal to x minus L over 2. That's it. So P multiplied by x minus L by 2, producing a clockwise moment at this cross section. Okay, so negative of P multiplied by x minus L by 2. Fine. What else? We have to deal with this P by 2 also. So P by 2 multiplied by this x, producing an anti-clockwise moment at this cross section. Hence a positive sign. P multiplied by P by 2 multiplied by x, or Px by 2. Same. Fine. So how can I write this? Let me write this in a better way. Mx is equal to, so negative of Px, positive PL upon 2. Okay, so we've got the positive value of PL upon 2, and negative of Px and plus Px by 2, and it would turn out as negative of Px over 2. Now it can be written in a better way. Mx, let me write this, is equal to taking P by 2 as common, and L minus x will be inside the bracket. Okay, fine. So what do we want? So let's say we have taken section between A and D. Let's find the value of bending moment at D. So bending moment at D will be equal to you can say that the value of x has to be taken as L by 2. So when x is equal to L by 2, you're going to find the bending moment at D, and when x is equal to this L, you're going to find the bending moment at A. It's that simple. So when x is equal to L by 2, we'll be getting the value of bending moment at D, and let's put in the value of x as L by 2. So L minus L by 2 is L by 2, so P by 2 into L by 2, that is P L over 4. Alright, and one more thing, when you keep the value of x is equal to what, L, you're going to get the value of bending moment at point A, this point. So the bending moment at A will work out as, again, x is equal to L, put it over here, L minus L will be 0, 0 into anything is 0, so the bending moment at A works out as 0. Now that all the calculation regarding shear force and bending moment has been done, we'll go ahead and make the corresponding diagram. Okay, so let's start off with SFD, shear force diagram. Let's have a baseline which essentially represents zero shear force. So any positive value will be taken above this, and any negative value obviously be taken below this. Okay, so starting from this VB, we have negative value, negative of P by 2. So this is point B's line minus P by 2. Okay, what about shear force at D? So the shear force at D in between section D and B is negative of P by 2 again here, negative of P by 2. What else? Now let's go ahead and let's work out the shear forces between section A and D. In A and D, we've got VD is equal to positive P by 2 somewhere here. Okay, now this distance is proportional. Okay, so you don't have to worry much about this. And finally, shear force at A is P by 2, positive value. All right, and when you join all of this with the help of simple straight lines, you're gonna have this. That's it. So this essentially is what you call the shear force diagram. This is negative shear and this is positive shear, you can say. All right, and the shear force is changing its sign at this point. Okay, at point D itself, or at a distance of L by 2 from either ends, from the left or from the right. Fine. Now let's go ahead and let's make the corresponding bending moment diagram. For that, I need to have a baseline. Okay, so this represents the zero bending moment, and anything above this will have the positive bending moment. So we've got the value of bending moment is equal to 0 at point B. So let's put in this 0. Okay, we've got bending moment at D is equal to PL upon 4. PL upon 4. We've got bending moment at D is PL upon 4. Okay, from the second section, that is section between A and D also, we've got the same value. And finally at A, we've got bending moment is equal to 0 here. That's it. When you join all of them, that's it. That's exactly what you're going to have. And if you watch carefully, this bending moment equation, mx is equal to P by 2 multiplied by L minus x, represents the equation of a line. Okay, and this is sort of a constant. And this Vx is equal to either, negative of P by 2 or positive of P by 2. This is sort of a constant. Okay, that's why a straight horizontal line or a vertical line. And here you see an inclined line, because this essentially represents the equation of a line. All right. So that's it. That's shear force diagram, and that's the bending moment diagram. And one thing that you can conclude is that when a beam is simply supported, then at the supports, that is at A and at B, you're going to have zero bending moments. Whereas the point where shear force changes its sign, the corresponding value of bending moment is maximum. So guys, that was all about SF and BM calculations. And I strongly advise you all to solve the same problem by sectioning from the left. I'm sure you're going to get the same values. Okay, go ahead and do that. We'll meet again with a new concept that I'm going to tell you. That is something which shows up the relationship between the load applied, shear force and bending moment, and it involves a lot of calculus. Okay, so that is something that I'll be taking up in the next video. Until then, it's a wrap. This is Manas Patnaik signing off. Take care. Have a great day. Keep learning.